a paper, Physical Time for the Beginning of the Universe. Well, okay, it's not actually written that well in English, but that's the rough idea. So I haven't read this paper, but it looks like it has something to do with a way that we can figure out what time is in the event that time itself arises. So let's read the abstract. So this is by Christof Wetterich, I guess, from Universität Heidelberg. The paper just came out a few days ago, 4 days ago. It's a preprint, so we'll see if this is worthy of publication, right? I mean, I'm not the one to judge, but we'll see. So, the abstract. We propose that physical time is based on counting the oscillations of wave functions. The discrete counting of the ticks of these clocks do not depend on the metric frame. It remains well defined for the beginning epochs of the universe. Okay. The photon clock counts the oscillations of electromagnetic plane waves in the cosmic reference frame. It can be gauged with clocks for other massless or massive particles. These equivalent clocks form a clock system which defines a common universal continuous physical time. That's important. For the photon clock, this physical time coincides with conformal time. The universe is eternal towards the past. For typical models of inflationary cosmology, the photon clock ticks an infinite number of times. We compare the photon clock system to geodesic physical time, which is a frame invariant generalization of proper time. Cool. Okay, so it looks like they're going to try to explain in the system of inflation, they're going to try to, which has an eternal past, they're going to try to explain how time arises. So, let's get into it. Let's just check on the centering, make sure that everything's A-okay. Excellent. So, time is a central concept for physics, and much work has been devoted to define physical time, both theoretically and experimentally. When it comes to the extreme situation in the beginning epochs of our universe, the concept of physical time may have to be rethought. This is a good point. So, when we start talking about like quantum gravity in the very, very early parts of the universe, I mean, gravity is about space-time, right? And so if space-time itself fails to be well-defined, or if it's in a superposition, you might have to rethink what we actually mean by time at all, which is very, very strange. So that's what I think they're going to try to solve here. There is no observer who can construct some clock apparatus under the conditions of the radiation-dominated epoch, or even earlier in cosmology. Right, yeah, you can't make a clock a fraction of a second after the Big Bang, right? There's no matter, there's just radiation. How should a physicist define time for these extreme early epochs? The present contribution to this question is based on numerous discussions I had with Valery Rubikov over the last 2 years of his life. They resulted in the publication 1 expressing our common view, with some points left out of our discussions left open. Okay, so let's go take a look at what this publication is. It might be related. Just scroll down and look at the references. Okay, so this was only published 2 years ago. Geodesic incompleteness in general metric frames. I'm not going to worry about reading it. Right. In general relativity, a physical time interval should not change under a general coordinate transform. So when we talk about physical time intervals, this is like the amount of time that would pass on your watch. Right, that is in like whether or not you're in a spinning reference frame, or regardless of how you're measuring that time, it should always be the same. You will always experience 1 second per second, say. Physical time has to be a diffeomorphism invariant. That's exactly what I was just saying. Basically, regardless of how you describe your system using coordinates, time and space coordinates, the actual amount of time is a physically relevant thing, not just a mathematical abstraction. Most commonly, one uses for physical time the proper time tau, measured by an observer moving on some geodesics, defined for particles with a fixed non-zero mass m. So the rough idea is that if you want to talk about how to measure physical time, you just imagine a clock is moving through space-time, and then you ask how many times it ticks. An alternative could be conformal time eta, which is associated to massless particles as photons. The proper time depends on the geodesics chosen. This is no problem as long as the proper times measured on 2 different geodesics can be mapped onto each other by an invertible map. All right, let's think about this. So, now, it seems like they're referring to proper time here, and yet they brought up conformal time. That's a little bit confusing, but maybe this was just an aside. But yes, the proper time does depend on the geodesics. This is the idea that if you're moving quickly through space-time, then you will record less time on your watch than somebody who doesn't move quickly through space-time. And then they say, well, okay, it's fine. It's fine if you have different proper times on two different geodesics. These are paths through spacetime. So long as there's like a relationship to connect one to the other. A given geodesic defines a reference frame. That's true. It basically defines a frame of somebody who's falling freely. The map between two inertial reference frames in flat space is given by the Lorentz transformations of special relativity. Yeah, bingo. In cosmology, one may choose a preferred cosmic reference frame, defined by the approximate isotropy of the cosmic microwave background in this frame. So this I should explain. The rough idea here is that the cosmic microwave background radiation is uniform in the universe. However, if you're moving, the part in front of you might be bluer than the part behind you, just because of red shifting and blue shifting, the Doppler effect. So the idea is that you can kind of fix a preferred reference frame by figuring out in which reference frame does the CMB look like it's the same color everywhere. By the way, for those who are just joining us, the paper is called Physical Time for the Beginning of the Universe. Right. So for a spatially homogeneous and isotropic universe, proper time in the cosmic reference frame coincides with the time t in the Robertson-Walker metric given by this. Now, we've seen this metric before. Again, this ds squared basically tells you it's the Pythagorean theorem rule, but for spacetime. So in general relativity, you describe spacetime with a metric, which is basically how to measure distances and times. It's the Pythagorean theorem. And so in general relativity, time contributes a negative to the distance. It's called a space-time interval, and space contributes a positive. So we have that this ds squared, that's like the c squared, and a squared plus b squared equals c squared. Then we have a minus dt squared. So if you travel through a lot of time, then your c squared gets smaller. And we have a plus, this term that looks like a squared of t dxi dxj delta ij. So this is just telling you that space is expanding with time. That's what that a of t squared is. And then this is just telling you that each unit of space is equal to one unit. It contributes one to the c squared part of the Pythagorean theorem. This is just saying that space is expanding in time because this a squared of t is increasing. And time itself, moving forward or backward, moving forward in time, contributes negatively to your space-time interval. So, so they're saying that in this preferred reference frame, the Robertson, this coordinate t actually corresponds to this, or sorry, let me rephrase. The proper time in the cosmic reference frame corresponds to the coordinate time t here. So, it is the proper time measured by a co-moving observer whose trajectory obeys dxi equals 0, meaning that they're just not moving in space. And they're using the standard sign convention where time is a negative and space is a positive. That's what this signature means. Branas, you're good. You're good. We just started. Don't worry. Don't worry. So, the notion of proper time measured on geodesics for massive particles has led to the concept of geodesic completeness. Okay, so so again, if you just got here, the title is Physical Time for the Beginning Universe. I feel like it should be the beginning of the universe, but how to say? Or, you know, who can say, right? So, right, where were we? The notion of proper time measured on geodesics for massive particles has led to the concept of geodesic completeness. They're going to explain this, but if they don't, I'll explain. A geometry with Minkowski's signature, that's this thing here. Time is minus and space is plus. A geometry with Minkowski's signature of the metric is geodesically complete if no geodesics stop at a certain point. So here, a geodesic is just kind of a free-falling trajectory through space-time. So think like an orbit. And if you're orbiting something and you don't have to use your engines or anything, then you have then you're in free fall, and that means that you're traveling along a geodesic. So they're just saying that if there's not like an abrupt end to a trajectory, then that means that your space-time, if there's not an abrupt end to any trajectory, meaning you don't stop at a singularity, if you don't stop at a Big Bang, whatever, on either end, either to the past or the future, then your metric is geodesically complete. So, That's just the definition of geodesically complete. For a Robertson-Walker metric, the criterion of geodesic completeness is that a of t dt is infinity. So they're saying that the total scalar function is infinite. And then they say for a finite integral, or t not extending to minus infinity, the geometry is geodesically incomplete. Basically, what they're trying to say is that if the scale factor gets to 0 at any point and then stays at 0, then you wouldn't have, then that means that the universe has collapsed to a point, either in the past or the future, and your space-time is geodesically incomplete. Alternatively, if there's like a minimum value, if like a of t is not well defined for, say, this is the scale function, by the way, it tells you how big the universe is. If the scale function is not well defined for some large negative value, meaning if you can't go past a certain point in the past, like if you can't go past the Big Bang, then you also don't have that as geodesically complete. So this is just a constraint for what it means for a metric, for a space-time to be geodesically complete in the Robertson-Walker metric. Now, a geodesically incomplete universe is often called singular, and it is believed that it cannot give its satisfactory description of the beginning epoch. So this is what I was getting at, roughly. The idea that, you know, if you wind the clock backwards, if you let a of t get smaller and smaller as the universe gets smaller and smaller as you wind the clock backwards, if you reach a stopping point where you can't make it any smaller, where it stops at 0 size, then it's geodesically incomplete. And that's exactly what they're talking about here. That's the Big Bang singularity, right? But it is true. It's believed that it cannot give a satisfactory description of the beginning epoch. There's problems with this. So, typical models of inflationary cosmology have been shown to be geodesically incomplete. So there are some models of inflationary cosmology. This is where you have like a rapid period of inflation and then a regular Big Bang afterwards. Most of these models end up being geodesically incomplete. This is related to the Borguth-Vilenkin theorem. And so the idea is that if you have a universe that's expanding on average, there will be a point where it reaches a 0 size as you wind the clock back. But it's not always the case. So this notion of geodesic completeness is a purely geometric property which only depends on the form of the metric. It does not involve any particle properties. So this is just geometry, right? It's just the geometry of spacetime. So in many models for the beginning epochs of the universe, scalar fields, these are like things like the Higgs field, the Higgs particle, play an important role as the inflaton, for inflationary cosmology. So the idea behind, are they actually going to explain it? Oh, they might explain it. If they don't, I'll explain. The dynamics of the cosmological solution involves then an interplay between the scalar field and the metric. Again, every time you see the metric, think of the geometry of spacetime. In the presence of a dynamical scalar field, again, scalar field, think of like a type of particle, and dynamical meaning changing. In the presence of a dynamical scalar field, pure geometric concepts for physical time, as proper time for an observer moving on geodesics, have to be questioned. Why? I don't understand why. So why must it be that if you have a scalar field that's dynamical, that you can throw, well, maybe they'll explain. It doesn't seem obvious to me why you can't still use geometric notions of physical time. Because the space-time it will just do whatever the space-time does. It doesn't matter what the scalar field's doing. But let's keep reading. In many models, the masses of particles depend on the scalar field, similar to the mass of the electron in the standard model, which depends on the value of the Higgs field. In cosmology, the scalar field phi of x, by the way, this is the letter that's often used for scalar fields. So in cosmology, the scalar field phi of x is not homogeneous in space and time. For a dynamical scalar field, it will depend at least on time, which makes sense. By the way, they're using x just to describe like all of the positions and times, like just all of the coordinates, right? In this case, the particle masses m of x become space-time dependent. This dependence induces an additional force, fifth force, that's a little bit sketchy, and particles, I see. And particles move no longer on geodesics. The trajectory is x, so this is how you can define the trajectory as like a set of coordinates as a function of some parameter. Obey now a generalized geodesic equation. Okay, so let me explain why now I understand. So The trick is that if the scalar field is changing with time, think of like the Higgs mechanism, right? The Higgs mechanism tells you what the mass of a particle is. So if you have an electron, but the mass is changing with time, or is changing with space, well, then roughly from Newton's laws, if the mass is changing, then the momentum has to change accordingly. In order to preserve momentum conservation, if the mass changes, then the velocity has to change accordingly. So what this means is that if the scalar field is changing with time, the masses are changing with time, which means that the velocities have to change with time in a way, meaning that you have non-zero acceleration. One way to think of this, by the way, like a good example, would just be imagine that you have like a wagon just like rolling along the ground, moving at some fixed speed. Say that there's like no friction. If you dump sand into the wagon as it's rolling, it'll slow down because it gets heavier. And so it would look like that there is some mysterious force that's slowing it down, but really all that's happening is that momentum is being conserved. So that's why using geodesics for proper time might not be the correct thing to do. So they're going to give us a different trajectory that any given particle will follow that isn't a geodesic. So here's the equation that they give. The trajectories obey now a generalized geodesic equation. So here, this is the normal geodesic equation. This is the acceleration, and this is roughly the force of gravity. And then there's a term that depends on the rate of change of the mass of the particle. And that's the important part. And it's actually really interesting that this is a term that appears. And so the rate of change of the mass is roughly this fifth force. Or at least it's what's contributing to this fifth force. Here they say that u with the subscript mu, that's just the speed relative to some parameter. And sigma parameterizes the trajectory. Yeah, so sigma is this parameter that tells them. Equation 3 is equivalent to the following. Okay. So equation 3 is equivalent to... My gain is a little bit high. Sorry, I'll move my mic. Equation 3 is equivalent to this parameter, namely that the velocity squared is proportional or is equal to the negative mass squared. Is that true? Why should that be true? Yeah, oh, okay. It's a mass-like parameter, but it's not actually the mass. So yeah. So this isn't actually the mass, it's a mass-like parameter. Only for constant m, equation 3 reduces to the geometric geodesic equation. Sure, that's fine. For general m squared of x, so they're just squaring the mass here, particle physics properties influence the trajectories in addition to the metric. This is easily understood by the presence of an additional force. So they're saying that if there is a scalar field that's kind of causing inflation, then there's an additional force, which means that, and actually they'll say this now, evaluating proper time on the geometric geodesics makes not much sense for particles or observers moving on different trajectories. So yes, g is the metric tensor. And sigma represents, it's just a way of parametrizing a curve. So you can think of it as like kind of like the length along that curve in some sense. So what they're saying is that, look, in the early universe, when you have a scalar field that's changing with time because of inflation, you can't even build a clock that travels along, like you couldn't even in principle build a clock that travels along a geodesic trajectory because the masses of particles are changing in such a way that geodesic trajectories are not non-accelerating trajectories because there's this fifth force that's changing masses. So what I suspect they're going to do is they're going to define this kind of cosmic time or whatever. Well, maybe they won't do this, but maybe they'll define like the cosmic time as like the path length along these modified geodesics. That's what I suspect is going to happen here. Right. In the presence of a space-time dependent scalar field, phi of x, the choice of the metric is not unique. That's interesting. Why? Why? Okay, well, we'll keep going. Maybe they'll explain. We could choose a different metric, g tilde, which is the metric, by the way. It's just a different spacetime metric, related to g by a conformal factor. So we have that our g tilde, these are the subscripts that just tell you like the entries in the matrix. And then you have this factor here, this w squared factor, which depends on the scalar field. So roughly something like they're just changing how we measure spaces and time, or distances and durations, by a factor that depends on the scalar field. They haven't explained why. So perhaps they'll explain. I mean, like you can always do that, but I don't know why they would. Again, for those who are just joining us, this paper is called Physical Time for the Beginning Universe. Came out 4 days ago. Okay, well, let's keep reading. Maybe they'll explain. The transformation from G to G tilde is a Weyl scaling or conformal transformation. Yep, that's true. The choice of the metric is called a metric frame. Okay, fine. If one computes proper time from the metric G tilde, it differs from the one obtained by G. That's not surprising at all, because if the metric changes, then the way you're measuring time changes. Proper time is not a frame invariant quantity. Yeah, obviously, if you change the space-time geometry, you're going to change proper time. Why? Okay, hopefully they'll explain. The geometric geodesics are obviously frame-dependent. Yes, I agree. And this extends to the notion of geodesic completeness based on geometrical geodesics. Okay, yeah, that's true. I agree. So they're saying if you rescale the metric by a certain amount, then it could be that the space-time which used to be geodesically complete might not be geodesically complete anymore, or vice versa. So we'll see. Typical inflationary models are geodesically incomplete in the Einstein frame, for which the coefficient of the scalar curvature in the effective action is given by the constant squared Planck mass. I see what they're doing. Okay. So, they're going to allow the conform. I think that they're going to allow the conformal scale, this conformal factor, to change the action. So, yeah. So typically, yeah. So they're referring to the Einstein frame. The Einstein frame is when your action is just a constant times the scalar curvature. But I suspect they're going to let it change, and that's why they're using a different metric. These models can be mapped by a suitable choice of W of phi to a so-called primordial flat frame, for which geometry becomes flat Minkowski space for t goes to minus infinity. So that is one moment, sorry. Thank you for the galaxy. Who sent this? Radu, thank you for the galaxy. That's huge. Enormous. Right. So they're going to choose a different frame that becomes entirely well-defined, even at large negative times, whereas typically the inflationary model is not geodesically complete. So they're kind of going to blow up, not explode, but they're going to like kind of spread out what you might have as a singularity at the beginning of time. Yes, inflationary models, at least most of them, do result in a singularity. So in this frame, the geometry is geodesically complete. Basically, they're going to choose a different frame. I don't actually like them calling it a frame. It's like a conformal representative or something. But they're going to choose a different frame where instead of having the geometry go to a point, go to a singularity, they're going to blow it up so it goes to flat spacetime in the far distant past. With geometric geodesic completeness, depending on the metric frame, one has to rethink this concept. Yeah, that's the whole point of what they're saying. Okay. In quantum field theory, wow. Okay, that's a jump. In quantum field theory, physical observables are independent of the choice of fields. Yeah, that's true. That's true. Basically, it doesn't matter what... this is roughly a coordinate statement. It doesn't matter how you're measuring things. Or it doesn't matter how you're describing things mathematically. What matters is what you can measure. This is particularly apparent for the quantum affection action gamma, which includes all effects of quantum fluctuations. Sure. Similar to the classical action gamma is a functional of fields, in this case the macroscopic or mean fields. The quantum field equations obtained by variation of this effective action with respect to the fields. For a given gamma, these are exact equations without any further corrections from quantum fluctuations. Sure, this is like, they're just kind of reviewing what the idea is behind how you can find the equations of motion in a quantum field theory. They're not going to give any details here because I don't think it'll actually be important, but let's see where they go. The correlation function, the connected two-point function, is given by the inverse second functional derivative of gamma. Now this is true. This is basically telling you how to get the, in some sense, like a probability of of a particle or of a field transitioning from one configuration to another configuration, you roughly just take two derivatives of the action. It's a little bit complicated to say, but this is a common thing that's done in a quantum field theory course. Higher correlation functions, vertices, are related to higher functional derivatives, such that the effective action contains the full information about all observables. Fine. Where are they going with this? This seems like out of the blue, but we'll see. We'll just keep reading and then we'll summarize and make sense of it. One can perform arbitrary field transformations for the macroscopic fields, which are the arguments of gamma. Functional derivatives are transformed accordingly, as well as the relations between observables and functional derivatives. They're basically saying that these observables are, in some sense, coordinate independent, which is fine. At the end, observables do not depend on the choice of macroscopic fields. See reference 8 for a recent discussion. Okay, fine. For cosmology, this basic property of quantum field theory has been called field relativity. Yeah, okay, so it's sort of like coordinate independence, but for fields. It states that the physics is independent of the choice of the metric frame. Oh, that's a big claim. I don't believe that, actually. Yeah, I actually don't believe this. I don't think it's true. So what they're saying is they're saying that because the metric is a field, and you could rescale the field. Well, okay, actually, no, let me rephrase. So, is the field an observable? No. So if we're thinking of the, if we're thinking of the metric as, if we're thinking of the metric tensor as as just a field rather than some sort of observable, I'm used to thinking of the metric as an observable, something that you can measure, or at least you can measure the effects of it, like curvatures. However, if they're thinking of the metric not as an observable, and they're not even perhaps thinking of the curvatures as an observable, yeah, observables are unitary operators typically, but let's go look at what the reference says. I mean, it's probably a long paper. The reference was written by the same author. That's a little bit suspicious. I might read this later, but you know, for now, we'll believe them. We'll believe them tentatively, but I'll explain why it's a little bit suspicious. So I can understand if you're treating the metric as a field rather than as just like a background geometry. However, it seems a little bit strange because that, like, you're talking about allowing distances to be, well, okay, if you're doing quantum gravity, maybe this is actually true. And then you can just do a different field description. But the claim is that physics is independent of the choice of the metric frame, meaning that you can just multiply the metric by whatever function you want, and the actual physics is the same, which I'm not sure if that's true. But let's believe them. Physics is not only invariant under general coordinate transformations, that's true. That's called general covariance. It's roughly the Einstein equivalence principle, which can be considered as a particular subclass of field transformations. It is invariant under arbitrary field transformations, including the Weyl transformations. So Weyl transformations are just this rescaling here. That is very, very suspicious, but we'll read. General coordinate transformations leave the geometry invariant, while this is no longer the case for more general field transformations of the metric. In the view of field relativity, geometry loses its fundamental meaning. Okay, so, oh, I know what they're doing. I know what they're doing. They're going to use conformal time because conformal time doesn't change based off of metric rescalings. That's what they're doing here. Okay, maybe this will work. I'm still not convinced, but if they're just looking at causal structure, they may actually get something. So it clicked. It just clicked. We'll see where they go. By the way, I'll like the live and stuff. Do the doobly-doo, right? Right. These considerations have an important impact on the possible definitions of physical time. Luna, thank you for the mirror. By the way, for those who are just joining us, physical time for the paper is called Physical Time for the Beginning of the Universe. And yeah, I can summarize. That's no problem. what they've been talking about is they've been talking about different ways that we can define time, namely in the presence of some sort of inflationary behavior, like during inflation in the early universe. You can't necessarily talk about time in the way that you would normally like to, because if you have an inflaton field that's changing with time, the geometry doesn't necessarily influence how you would measure time. Rather, it's the inflaton field would affect that because it'll affect masses. So that's roughly the idea. So I think that they're roughly going through to try to figure out if they can come up with a more invariant way of defining time. Right. Okay. So they say, these considerations have an important impact on the possible definitions of physical time. Physical time should be a frame invariant quantity. Okay. So I'm not this author. Maybe this author is brilliant. However, I would never put an exclamation mark in a paper that I'm writing. That seems a little unprofessional. Maybe? I don't know. Not unprofessional. Like, it just seems like he just seems really excited. Yeah. But we'll continue. Yeah, it's like in the same way that we don't write in first person, right? Anyway, as we have seen, this is not the case for proper time. So right, proper time is not frame invariant. We propose that the central concept for physical time is the counting of oscillations of some periodic process. That's actually quite reasonable. The idea is if you have some periodic process, then we just count how many times it oscillates, because that will be some physical thing rather than relying on some geometry, which may be loosey-goosey. This is actually the way how one defines the time standard on Earth. One counts the number of oscillations of the radiation emitted by some atomic transition. Yeah, this is an atomic clock, right? Atomic clocks, you take a cesium atom, you heat it up, and then you bombard it with microwaves, and then the microwaves will excite some of the cesium atoms, and then they'll be re-emitted, and they'll emit a certain frequency of light, and then that light is basically that light tells you exactly how long time is by base. The frequency of that light is how we measure time, basically. I have a video on it, go watch it. Anyway, we may define the periods by the zeros of some field component, e.g. the electric field of the radiation. Sure. If these zeros are mapped to zeros in an invertible way by a field transformation, the number of zeros remains the same. Okay, this is actually a good point. So the point is if you rescale, if you do all these field redefinitions, or these field transformations or whatever, maybe you're even rescaling the metric, whatever it might be, so long as the transformation is invertible, meaning that you can do it and then undo it, then the amount of zeros of the field components should be unchanged. And so it should be a physical observable. In fact, they say this here. This is realized by the frame transformation of the metric. By the way, this will be posted. I will be uploading this on YouTube tonight. So physical time defined by the number of oscillations in a frame invariant. Oh, physical time defined by the number of oscillations is a frame invariant quantity. Cool. Yeah. So the point is you have some field. A field is just a number at every point in space. So if you count the number of times that number gets to zero, passes through zero, and then comes back to zero, if you count the number of times that it passes through zero, then the number of zeros should be unchanged regardless of how you do field redefinitions. So this seems plausible. Right, okay, so oscillations occur in early cosmology. Okay, so they're going to try to do oscillations. They're going to try to count time with oscillations in something. For example, we may consider the wave function for the photon of the associated electromagnetic field in the cosmic rest frame, which obeys the field equation. This. So here we have is this the wave function? I guess this is the wave function as a function of momentum. And here, yeah, okay, this is the wave function as a function of momentum, fine. Here we have two conformal time derivatives. Then we have, what's this h here? Oh, it's a conformal factor, or it's related to the scale factor. And then we have the momentum here. This is just the, I guess that this is like the, what? What's the scalar field? What's the vector field equation? It's roughly the wave equation for, well, it is the wave equation for vector fields in an expanding universe. Anyway, so they say that eta is conformal time, and it's defined by this. So you basically rescale the regular time coordinate by the scale factor. So if the universe gets smaller, the conformal time gets smaller. Sorry, is that true? If A is big, then the conformal time is small. Yeah. So as the scale factor gets smaller, conformal time gets bigger, and vice versa. H here is just a derivative. It's a time derivative of the scale factor. And then, why are they writing what G is? We know what G is. Okay, this is the metric in conformal time. So the metric in conformal time is just Minkowski space. So if you just take Minkowski space and then rescale it with conformal time, you get the Robertson-Walker metric. This is not the Hessian. No. It's close. It's the D'Alembert. It's the D'Alembert operator. Okay, and then k squared is the wave vector momentum for a plane wave. Okay, so this is the wave equation for a plane wave, or this is just the wave equation for a vector field. That's all. Okay, so this is the equation that a photon satisfies, or equivalently that the electromagnetic field satisfies. That's all that matters here. So, yeah, so the field, phi of k, stands for some component of the electromagnetic field in Fourier space. Totally fine. It can also be a component of the graviton wave function or any other massless field. Okay, fine. An arbitrary electromagnetic field, for example, the one of the CMB or the photons in the radiation-dominated epoch, can be composed as a linear superposition of Fourier modes phi of k vector. Okay, fine. So they're basically just telling us that they're going to be describing some electromagnetic field, and all of them will satisfy this. For defining a clock, we focus on a particular wave number k. So they're basically just going to imagine that they have some photon, some electromagnetic wave, that has a particular momentum. Fine. For a given wave number k, the solution of the wave equation 7 is a standing wave, which reads in position space this. So it has an amplitude. That's what this B of eta is. It just tells you how strong the electromagnetic field is. And then it has an oscillatory component. So it travels, okay, yeah, they're assuming C is 1. That's fine. So this is just the standard exponential notation for a traveling wave. I don't know why they call it a standing wave when it's very clearly traveling, but okay. I'm not going to complain too much. Also, they forgot a dot here, but that's fine. The smooth function B of eta accounts for the Hubble damping. So essentially, because the universe is expanding, the amplitude's going to get weaker. Well, there's no boundaries here, so it can't be reflected. There's nothing to bounce off of. It's just a plane wave, which is fine, but it is traveling. It has it moves, and it is a traveling wave, but it's fine. This is a preprint. It's okay. For high momentum modes with k squared much greater than h squared, the function b is essentially constant. So basically, if your wave is oscillating sufficiently quickly, then the expansion of the universe doesn't actually play a role. For a given position x, one can count the number of oscillations n sub k vector. Discrete physical time is proportional to the number of oscillations, where the proportionality coefficient sets the time units. So roughly, they're saying if you're at a place, you just count how often the wave passes by you. It's going to go up, then down, then up, then down, then up, then down, and you just count the number of oscillations. Now it says plane waves with two different k's constitute different clocks. The number of oscillations is not the same, but they're proportional to each other. That's fine. One might oscillate twice as fast, but that's going to be fixed throughout all of space and time. The number of oscillations, n sub k1 of the first clock, is related by an invertible function to the number of oscillations nk sub 2 of the second clock. Yeah, there's just a one-to-one relationship. One might be double the frequency of the other. Different clocks can therefore be gauged in order to define a unique time by choosing appropriate proportionality coefficients. So essentially they're saying, look, you could choose a different clock, but that's just, it's like an arbitrary choice, so just pick one, and then all of the other clocks can be determined by some fixed relationship. This is the first example of a clock system. We call a clock system an ensemble of clocks for which the ticks of any pair of two clocks can be mapped to each other by an invertible function. Yeah, so roughly they're just saying, look, you might have a whole bunch of different plane waves of electromagnetic radiation, electromagnetic waves. You can relate the ticking rate of any one of those electromagnetic waves to the ticking rate of any other, just by dividing or multiplying by some constant, which is the invertible function here. It can be seen as an equivalence class of clocks. For the clock system of the photon waves in the cosmic rest frame, a useful continuous physical time is conformal time eta. For the high momentum modes, the number of oscillations is proportional to eta. So yeah, this is true. This is just the number of ticks is proportional to the conformal time eta. So k being just the wave number, and then you divide by a number to get the number of oscillations. Continuous time can be seen as the limit of discrete time for very large number of oscillations. Yeah, okay, that seems fine. Essentially, you can divide by k on both sides. If k is very, very fast, or if k is very, very large, then you'll get essentially continuous eta, because you'll be dividing by a very, very big number, which means that you'll have a very, very small number, which is close to continuous. Okay, so we'll get, are there no sections in this paper? Oh, this is terribly organized. It's fine. We'll get to a good stopping point, and then I'll do a summary again. So, the clock system of photons can be extended to include oscillations for gravitons or any other massless field. One might ask what happens for the oscillations of the wave function for massive particles, or for oscillations in different reference frames. Do they belong to the same clock system as the photon clock, or do they constitute different clock systems? For late cosmology, the map between all these different clocks is invertible. So this is an important point. They're saying that at late time, like when we exist now, it doesn't really matter how you use your clock. You can go from one to the other in basically between any number of clock systems, because I guess the mapping relationships are all, invertible, smooth, one-to-one, these lovely things. However, I suspect the answer will not be the same for early times. Right, all the clocks are in the same equivalence class. At late times, we can express the number of ticks in terms of conformal time eta. For example, the ticks of an atomic clock on Earth can be expressed in terms of a corresponding interval of conformal time. Sure. Similarly, proper time of an observer moving on geodesics or on more general physical trajectories can be expressed in terms of conformal time. Sure, you could always do that. The issue of equivalence concerns the beginning of the universe. For the photon clock system, the physical time towards the beginning of the universe is infinite for many models. For common inflationary models, conformal time extends to negative infinity as one moves backward in cosmic time or some other time variable. The number of ticks of the photon clocks is infinite since the beginning. So the idea is that if you have an inflationary model, in some sense, the ticks get closer and closer together in conformal time as you go back to like the singularity until there's an infinite number of ticks going back. The time interval, they're saying this here. The time interval between two ticks shrinks if one uses cosmic time towards the beginning, while it remains constant for conformal time. Still, the number of ticks is the same in the two frames. If one uses the photon clock system for the definition of physical time, the universe exists since infinite time. It is eternal. That's an interesting point. Namely, it depends on how you define time. Maybe you shouldn't have been using cosmic time for your definition of time. You should have been using conformal time, because conformal time maps nicely to physical time, to cosmic time in the late universe, but it doesn't map nicely to cosmic time in the early universe. In contrast, for clocks defined by massive particles moving on suitable trajectories, the number of ticks may remain finite in the limit where eta goes to minus infinity. So it might be the case that for like matter particles, like electrons or whatever, the oscillation of their wave function, it might not oscillate faster and faster as the time goes back. So we'll see what they say. In this case, these clocks belong to a different clock system, right? Because there's no mapping between infinity and finite. So then they wouldn't be in the same clock system. The map from such massive particle clocks to the photon clocks does not remain invertible for eta goes to minus infinity. Exactly. The issue of inequivalent clock systems is directly related to the question, does the universe exist since infinite physical time? Yeah, so this is what I was just pointing out. The question is how do we define physical time? In the late universe where we exist now, it's totally fine because every clock is the same. But a photon clock is different from, say, a particle clock in the early universe. So which one is like the actual real time? Which one is actually physical time? So that's the question here. In reference 1, we have studied the clocks for massive particles in detail, in particular the case where the masses depend on some scalar field and therefore on time. This leads to the concept of a frame invariant generalization of proper time for particles moving on generalized GOD6. Okay, I believe that they would have done that. We have found in some cases for massive particles that are not equivalent to the photon clocks. This will bring us to the question, which clocks are most useful for a definition of physical time, which we will discuss at the end of this note. Our investigation has suggested a frame invariant generalization of the notion of geodesic completeness, namely time completeness. Interesting. The universe is time complete if physical time is not bounded towards the beginning or end. The clocks defining physical time never stop ticking neither towards the beginning nor towards the end. If there exist inequivalent clock systems, time completeness will depend on the choice of the clock system. We briefly summarize here the results of reference 1. Okay, so they're about to summarize what they did in the first reference, but let me explain. So the question here from the very beginning is roughly, they're trying to figure out how we measure time in the early universe. And they made an argument, which is fairly convincing, that if you, in an inflationary universe, which is one of the better models for how our universe got to be the way it is today, that it inflated very rapidly near the beginning of quote unquote time. In an inflationary universe, the way that we account for time isn't particularly well defined, or it's not a particularly useful way to account for time in the very early universe. And so, furthermore, if the notion of space and time itself is not particularly well defined in the early universe, which it might not be, then you need some way of accounting for physical time, in a way that doesn't care about how you're representing your geometry, like what kind of variables you're representing your geometry with. And so they say, well, one way that you can do this is just count how many times a thing oscillates. Totally reasonable. That's how we define time today. So imagine that you have like a beam of light. Every time the beam of light every time the beam of light has 0 amplitude, you make a tick mark, and then every time it reaches 0 again, you tick again, and that's the ticking of your clock. However, there are other ways that you can measure time, which is, say, the wave function of matter field. So like think of like the quantum wave function of an electron. It'll occasionally pass through 0 as well, and you can count how often that passes through 0. And those might give you different notions of clock. And so the question is just which clock should you use? That's really what they're trying to answer here. But they're going to summarize reference 1, which is where they discuss the clocks for massive particles. These are like the clocks for like electrons, say. So let's see what they have to say. Let's read their summary. Right. Consider the clocks defined by a free scalar field with mass m. Okay, so they're not actually going to worry about electrons, they're just going to worry about some free scalar field, so like a Higgs boson kind of thing. They're going to have a minimal coupling to gravity and canonical kinetic terms. So they're basically saying that it doesn't it doesn't do anything fancy to gravity, it just does what it usually does with mass. The field equation for a scalar field with mass depending on the spacetime coordinates x reads this. So yeah, so this is just the D'Alembert. It's the wave operator on a massive field. This is that m is the massive field, but here the mass is allowed to depend on the position because that's affected by the inflaton field. Here that d sub u is the covariant derivative in presence of the metric. This is basically just a way of defining a partial derivative in a space-time in like a nice geometric meaning. And g mu nu is the inverse metric. So this is roughly the space-time equivalent of the Laplacian operator, or the divergence of the gradient. So they're looking for fast oscillations because they don't want to take into account the expansion of the universe. And so they say that So this is the ansatz that they're giving for their scalar wave equation. Sorry, their scalar fluctuations. Why not two covariant derivatives? One covariant, so partial derivative on a scalar field is already covariant, so you don't need two. It's just lazy though. They definitely should have just written D. They should have used the same symbol because it just makes it confusing. Right, so they're looking for fast oscillations, and this is the form of their scalar field. So they have an amplitude, and then they have an oscillation. Fine. Where S of x obeys this equation. So basically, you take this equation, you plug it in here, and you'll get an equation for S. That's all you need. And roughly, it's just saying that the square of the length is proportional to the mass squared. Sorry, the square of the derivative of the phase is proportional to the mass squared. And they also find that a of x is just some function that changes slowly. So it's not like the amplitude of the oscillations in the scalar field are very, very slow. Like they're basically the same amplitude across space and time. Since equation 12 is invariant under Weyl scalings, the quantity S of x is frame invariant. Now, this is something that would have to be checked. However, it actually follows trivially. Yeah, it follows trivially because, it follows trivially because these are partial derivatives, so it doesn't pick up on the actual curvature. So that makes sense. Okay. So this is invariant under Weyl scalings. So this is so S of x is a frame invariant, and S of x, by the way, is telling you where the thing hits 0, which is exactly what we want. For counting oscillations, we have a tick of the clock whenever S decreases by 2 pi. That's exactly it. So the idea is that S is the function that's going to tell us the clock for our matter field. It's going to decrease, or it's going to it's going to either increase or decrease, whatever it's doing, but every time it changes by 2 pi, you have a tick, because that's telling you the phase. It's roughly where on the wave you are. The definition of a clock needs a trajectory on which S is evaluated. So S is a function that is defined everywhere in space-time, so you need to measure that along some sort of trajectory. In the late universe, we may identify X with the trajectory of an observer. So just like have a person hold on, or like measure the wave function phase, along some path that they're moving along. By the way, wait, hold on, this is weird. Phase is supposed to be okay, this is not a quantum field. This is not the wave function of a quantum field. This is just a classical scalar field, and that's important because in quantum mechanics, the phase is not observable. So this is a classical field here. Very important. Right, okay. In the late okay, so they're just saying that in the late universe, we may identify X with the trajectory of an observer. Okay, so somebody's just gonna float through space, measuring the amplitude of the field, and they're gonna see when it crosses 0, that's a tick on their watch. The oscillations of the scalar field are given by the solution of equation 12, sure, and do not depend on the presence of an observer, while the number of zeros seen in some interval of sigma depend on the trajectory. We can replace the observer by a particle moving on the trajectory x. Fine. This definition of a particle clock can be used for early cosmology. What particle? Is it a particle of this field? Probably. Yeah, that's probably what it is. A given trajectory defines a reference frame. Fine. For a given solution for S, there exists a large family of clocks defined by different reference frames. Our concept of physical time related to the oscillations of some field induces in a natural way the notion of reference frames. So the idea is that you can have a whole bunch of different trajectories, but so long as it's for the same field oscillations, you can relate the number of zeros in each for different trajectories to each other, which is fine. So that gives you an equivalence class of clocks. If cosmology is homogeneous and isotropic in the average, that's a weird sentence. If cosmology is homogeneous and isotropic in the average, one possible choice is the cosmic reference frame. Sure. It is given by a co-moving trajectory with constants xi, so this is, and Yeah, okay. So this is just the yeah, it's given by co-moving trajectory with constant xi and x naught equals c sigma. So this is just the idea that it's stationary with respect to the cosmology, meaning that the cosmic microwave background radiation isn't redshifted or blue shifted. We could also use the physical trajectory of particles with mass m of x, which obey equation 3, defining the generalized geodesic. So again, remember that the masses can change, which gives you sort of a fifth force. And so you have to, you can't use standard geodesics to measure time, but you can use these other generalized geodesics for changing masses. You can do that as long as your mass function is well defined. Yeah, they say it here. For m bar of x equals m of x, a particular clock counts for a massive particle moving on a generalized geodesic the number of oscillations of its own wave function. Sure. Again, for those who are just joining us, the title of the paper is Physical Time for the Beginning Universe by Christof Wetterich. Wetterich? Where were we? Down here? Right. This geodesic physical time is analogous to proper time for an observer moving on geodesics. In contrast to proper time, the ticks of this clock are frame invariant. Right. So is this true? Yeah, so if you do a rescale it, actually, is this, hold on. Why is this true? I buy it for the electromagnetic wave because those travel along null geodesics, which are invariant under rescalings. However, why is it true for massive particles? Did they explain that somewhere? Contrast for clocks defined by massive particles. So why is it fixed? This leads to the concept of frame invariant generalization of proper time. Well, okay, let's think. So if you rescale the metric between two spacetime points, why wouldn't the scalar wave function not also change if it's that's why. Right. It's because this equation, which tells you where the it's not, there's no calculation to be done. It's because this wave equation that tells you how the scale or how the phase changes with time and space is scalar or is Weil scaling invariant. So it's because equation 12 doesn't change when you do a rescaling of the metric. And equation 12 tells you where the zeros are. And so you'll have the same number of zeros. So long as you don't have to account for the expansion of spacetime, which means that you have fast oscillations. So that's what's happening. So we have geodesic physical time, which is similar to proper time for an observer moving on geodesics. In contrast to proper time, the ticks of this clock are frame invariant. Okay, so far so good. Interesting. That's how you get the brain juices going. Okay, they're going to focus on precisely those cases, the geodesic physical time, where a particle is measuring the phase of its own wave function. We focus on the following: m bar equals m. In this case, a family of generalized geodesic trajectories can be related, they're citing themselves, to the solution for s of x by this equation. So we have the particle velocity is related to the phase velocity, or to the rate of change of the phase. Fine. Why is that true? Oh, no, okay, that checks out. That checks out, because of course the phase changes at a rate proportional to its velocity. It's a wave equation. Of course. From equations 13 and 14, one concludes that... What does this mean? From equations 13 and 14, this is we haven't done equation 14 yet. This might be a typo. Anyway, one concludes that d sigma involves the geometric proper time interval d tau. So this says that d sigma, which is just the parameter along the geodesic, is related to d tau by the mass, essentially. Yeah, okay. Oh, and this follows from just the geodesic equation that we had somewhere else. Here. Follows from this equation. They meant equation 5. If you combine equation 5 with equation 13, then you get equation 14. This just tells you that your parameter along your generalized geodesic is related to the actual proper time, the geometric proper time. Again, for those of you who are just joining us, the paper is Physical Time for the Beginning Universe. Neither d sigma nor d tau are frame invariant. Okay, that's obviously true because there's a g there and g changes when you rescale the metric. If we compute the number of ticks of the clock, however, we find a frame invariant quantity. Okay, so we kind of already believe that the number of ticks of the clock are frame invariant. However, let's just see what their calculation is. So we have the number of ticks on the clock. Sorry, we have the phase at sigma minus the phase at sigma naught. This is just an integral. That's totally fine. This is just the fundamental theorem of calculus. You guys should recognize this if you're taking calculus. It's just the fundamental theorem of calculus. But we know what d sigma, what the partial derivative of sigma with respect to x mu is. It's just m squared. How do they follow? How do they get that? That's not obvious. It should be related to this. Why is it m? Oh, they're just using equations 13 and equation 14. Okay, that's fine. Totally fine. And then they use that d sigma is related to d tau in this way. So we get just that m is related to, or that the amount of ticks roughly is related to the geometric proper time integral of the mass. So they define a geodesic physical time, t, by minus ds, or rather roughly minus s, which is related to the mass times the proper time. Which is interesting, because if the mass changes, so what they're saying is that as the particle's mass changes, if the particle's mass increases, then the rate at which time ticks increases. Interesting. That, at least for this definition of geodesic physical time. The frame invariant generalization of the proper time interval, m of x d tau, has been proposed in references 11 and 10. Let's see if he's citing himself. He probably is. Oops. Himself. And not himself. Actually, this is these are huge names, so I suspect this is probably a good paper. It's probably quite good. He's not just citing himself, so it's okay. Again, for those who are just joining us, the paper's title is Physical Time for the Beginning Universe. Right. Since geodesic physical time is invariant under Weyl transformations, it can be evaluated in any metric frame related by such transformations. One may introduce time units by multiplying the dimensionless dt or delta t with a suitable proportionality constant. For constant m, geodesic physical time coincides with proper time. So what they're saying is that if the mass of the particles doesn't change, then this really is just regular proper time. But in the early universe, where the mass of the particles can change, then you have some issues. So maybe you want to use geodesic physical time rather than proper time. Fine. I'm going to drink some water. By the way, consider subscribing. Support the live. It's, I have stuff in my link tree if you want to do that. Right. Let's continue. For a given solution, phi of x or s of x of the scalar field equations 10 or 12, 10 or 12 are these, remember? It's just the field equations for the field or the equation for the phase. There are many trajectories which obey equation 13. This equation here. For these trajectories, we can still count the periods and define dt, which is again, an infinitesimal step forward in time, by the negative change of the phase. The relation 16, however, does not hold. Why not? That's confusing. Wait, did I just skip something? I think I skipped something. Yeah, I definitely skipped something. Hold on, I just skipped forward for some reason. For a given solution of the scalar field equations 10 or 12, there are many trajectories which obey equation 13. These trajectories are distinguished by initial conditions. Okay, sure. For all of those trajectories, equation 16 is valid. The clocks tick differently for different trajectories since m of x and d tau have to be evaluated for a given trajectory. Furthermore, there are many trajectories which obey the generalized GDC equation, but do not obey equation 13 being this thing. For those trajectories, we can still count the periods and define dt equals minus ds. The relation 16, however, does not hold, meaning that it's not necessarily one of these nice trajectories. Why? Okay, hold on. Let's think about this for a minute. Many trajectories which obey equation 13. For all those trajectories, equation 16 is valid. Sure. So if they obey equation 13... Ah, I see. So not all of the trajectories obey equation 13, which means that they don't obey equation 16. Okay, fine. All solutions of the generalized geodesic equation define clocks in different reference frames. Okay. The question arises how the clocks in different reference frames are related. For flat space, constant m, and two trajectories. For flat space, constant m, they're missing an Oxford comma. And two trajectories specified by the four momenta p mu and q mu of a mass particle, one can show that the time intervals delta t in the two reference frames are related by a Lorentz transformation. Yeah, okay, so this is saying that if you're in flat space, your mass isn't changing, and you have different initial speeds, then the amount of time between two moments, I guess, for the different trajectories will depend on you can relate them via just kind of time dilation, right? Roughly. The general case with space-time dependent metric and mass can be rather complex. One finds that clocks defined for different reference frames are not always equivalent. They may belong to different clock systems. There's no universal particle clock. Okay. Another interesting issue concerns the question with which particle clocks belong to the same clock system as the photon clock. So it seems like what they're saying is that when we have when the masses are changing, then maybe we can't use particle clocks because they're just not particularly good. Like there's a whole bunch of different varieties and we don't know which one's the best one. Maybe that's what they're about to say. We demonstrate these issues for a homogeneous isotropic cosmology with a Robertson-Walker metric 1. The Robertson-Walker metric was this that we showed earlier, just an expanding spacetime. Where are we? Down here. And m depending only on time. So the mass is only changing with time, it's not changing with space. That would make it very, very messy. The wave equation 7 receives an additional contribution for massive particles. So this was the wave equation for photons. Right? Yeah, this is for photons or electromagnetic waves. However, now I'm confused. What metric is this? The wave equation receives... Oh, no, okay, this is fine. This is fine. Still just a wave equation. Still just the wave equation, but this was for photons. Now they're imagining they have a massive particle instead. Totally fine. No problem here. Right, so then you can compute the phase. This results in a phase and a rate of change of your phase. For the rapid oscillations of interest, both a squared m squared and d eta of h are small compared to k squared. So basically, this term... This term and this term are both small if k is really big, if something's oscillating very, very quickly. Then you can make this assumption. Thank you for the sub. Who just subbed? Hot Sauce and Astral Fine, thank you for the subs. And Mac, thank you for the subs. Everybody, thank you for the subs. That's cool. I appreciate it. Right. Right, so if you have rapid oscillations, then these two terms drop out, and the solution of the field equation approaches the one for massless particles fine, because the one for massless particles is just this. So if m is sufficiently small, or if the oscillations are sufficiently fast, then it behaves like a massless particle. Let us first consider the cosmic rest frame with trajectory x0, so it's just moving forward in time, not moving through space. Physical time is then given by this equation. So remember, This is the relationship between speed, or velocity, and the phase, partial derivative of s with respect to x. And because the position isn't moving, the only partial derivative we have is with respect to conformal time. And so that's why our phase is given by this integral. It's this integral just simplified, because we know that dx mu is just dt, or rather d eta. And so that tells us which partial derivative we can take. And then, because we already know what the derivative of d eta is of s tilde, we can just plug that in. And so they say for all solutions with k squared greater than 0, the physical time interval delta t diverges as the initial eta, the first moment, goes to negative infinity. So the idea is, yeah, so these clocks are time complete, meaning that the clocks of these massive particles goes back forever. There is no finite past for these. They belong to the same clock system as the photon clock. So even with massive particles, it sounds like what they're saying. Yeah, even with massive particles, some massive particles anyway, they belong to the same clock system as the photon clock, which is great. In particular, if a squared m squared approaches 0 as the conformal infinity goes to minus infinity, the ticks of the particle clocks coincide in this limit with the ticks of the photon clock for the same k. Great. So this is lovely. So this is one class of particle clocks that coincides with the photon clock. However, I imagine they're about to tell us about another one that doesn't. We next consider the clocks for trajectories corresponding to the generalized GD6 for the massive particle. So this was just for a particle in the cosmic rest frame. However, there are other particles and other moving along other trajectories that they're going to consider here. Right, so they're going to consider the clocks for trajectories corresponding to the generalized GD6 for the massive particle. So again, this is the generalized GD6 equation. Where is it? So they are solutions to 13, but they also travel along generalized GD6. So the generalized GD6 were... Wait, now I'm confused. Equation 13 wasn't for generalized G... Oh, no, it was for generalized GD6. That's right. Okay, fine. For those who are just joining us, the title of the paper is Physical Time for the Beginning Universe. Right, so they have another trajectory. This is just another generalized geodesic that massive particles can travel along. If the mass is changing, then, the geodesics are not standard geodesics. This is just one of the solutions for these geodesics. It tells you how the velocity changes. So here we have that it's traveling through time at this rate, and it's traveling through space at this rate. Roughly, the rate at which it's traveling through time is depends on the rate at which it's traveling through space. It depends on the rate at which it's oscillating, and the rate at which it's traveling through space is proportional to the rate at which it's oscillating as well. Did I cover what is a geodesic? I'm actually going to make a video on that tomorrow, but a geodesic is just a trajectory through space-time. That is kind of like natural. It's the trajectory that you would take if you just did nothing, if you didn't turn on your engines, if you didn't, move or anything. It's just the one that you just travel along when you just go. Anyway, one infers from equation 16, the geodesic physical time interval. It's this equation here. The geodesic physical time interval, dt, is this. So we want to compare that with this delta t that we calculated here. It says it differs from the result for the cosmic rest frame. Roughly, we have this integrand here, square root k squared plus a squared m squared. And then we have this integrand here, where we have a square root k squared plus a squared m squared in the denominator. If a squared m squared remains finite for eta going to minus infinity, the geodesic physical time is equivalent to the one defined by the photon clock. On the other hand, if a squared m squared goes to 0 as the conformal time goes to negative infinity, then you can take the limit of this. You can evaluate the clock, and then you find, one has that this is the delta t. So you're just integrating this equation so long as am is proportional to the conformal time to some negative power. When this is the case, the geodesic physical time interval remains finite for the initial, for a negative conformal time going to infinity if alpha is greater than or equal to 1. Sorry, greater than or equal to a half. So what we're saying is, in this case, the particle clocks on trajectories given by the generalized geodesics do not belong to the same clock system as the photon clock. Because basically, this delta t doesn't go to infinity as you wind the conformal clock back, whereas the photon clocks do. They are not time complete or geodesically complete in the generalized sense. For example, this happens for de Sitter space with constant m where alpha equals 1. Since dt is frame invariant, the same happens in the corresponding primordial flat frame where a approaches a constant for eta going to minus infinity while m vanishes in this limit. So all they're saying there is they're just giving an example of a case where this does happen. Like, this is not some like super ad hoc thing. In a very, very simple spacetime, the de Sitter spacetime, this does happen where you have particles not matching the same clock type as the photon clock. Right. One would like to understand why the particle clocks on generalized geodesics can stop ticking for eta going to minus infinity, whereas the photon clocks tick at constant pace. This is best. So, okay, so now hopefully they're going to give us some intuition here. Because basically, as you wind the conformal time back, the photon clocks tick at constant rate. And so because the conformal time can go backwards forever, you get an infinite number of ticks on the photon clock. However, for some particle clocks, their ticking slows down as you get further and further back so you end up at a finite number of ticks after an infinite amount of conformal time. This is best understood in a frame where a is constant, while m vanishes for eta going to minus infinity. With a equals 1, conformal time equals cosmic time, and the photon wave functions are simple plane waves. Fine. In the lowest order of m over k, so again, this is just an expansion they're doing in the mass of the particle divided by its momentum, roughly, or its wave number, the particle wave function obeys this. Okay, I'm going to believe that they solved the differential equation. I kind of believe that. It seems plausible. Yeah, so this is massless. This is the massless term, and then you'd have some... yeah, okay. Okay, this is plausible. This is a contribution from how much... from the mass, essentially, whereas this is what you would have if it was massless. So this is plausible. Basically, the mass contributes to a negative factor of the ticking. It slows down the ticking a little bit. The wavefront s equals 0... x vector equals xw times k vector over k. What does that mean? That's terrible notation. This obeys... okay, so... what are they trying to say? What are they trying to say here? Why are they saying x vector equals xw k vector over k? It might just be a definition. They might just be defining... oh, they're telling us... wait, what are they saying? What are they trying to say here? I see what they're doing. They're finding the position of the wavefront, defining it in terms of xw. So here, s is the phase, so they want to figure out where the phase equals 0. So they're just setting the left-hand side to 0. And then they're trying to figure out roughly how far in terms of the wave vector you have to go to get to that point. So they just set this to 0. They write x vector equals xw times k vector over k, and then they just solve for xw. So that's how you just get eta plus this term. So you're just solving for xw in this equation by setting the left-hand side equal to 0. And then they also get a relationship between about the normal derivative, sorry, not normal derivative, the conformal time derivative of xw, which is roughly how quickly the wavefront is moving with time. And it's just taking the derivative of this, right? So you get a 1 there because it's just the derivative of x with respect to x, essentially. And then you have to use the Leibniz integral rule to find the derivative of this term here, but you end up just getting m squared divided by 2k squared. It's how it works out. The trajectory of the particle moving on generalized GOD. Okay, so here's the point. So, yeah, so the rate at which the clock ticks, the rate at which the clock ticks is roughly given by this equation here. And the mass affects the rate at which the clock ticks. It's important. The trajectory of the particle moving on generalized geodesics. So this is, they're just doing another variable redefinition, can be characterized by its velocity. So this is roughly the position of the particle in some nice units. And I guess you can just take the derivative of this. How are they evaluating this? What equation are they using? I think that they're using this. Yeah, they're using these equations. Yeah, okay. And and they're assuming that k is large. So they can take the limit as k goes to infinity, or rather as m over k goes to 0. Yeah, in lowest order in m over k. Fine. Position to velocity would be an integral. Yeah, it would be. No. Position to velocity would be a derivative. You differentiate position to get velocity. So when m is greater than 0, i.e. if the mass is 0, if the mass is positive, the particle is slower than the wavefront. So the wavefront moves at this rate. However, the particle moves slower because the derivative with respect to eta of xp is less than the derivative with respect to eta of xw. In the reference frame of the particle, one can count the oscillations of the wave function which overtake it. So the idea is that your particle's traveling along, but the waves are passing by even faster. And so you can just count how often the wavefront passes by you. These oscillations determine the ticks of the clock in the particle rest frame. In the limit where m goes to 0, the particle velocity and the wavefront velocity approach each other. From the point of view of the particle rest frame, the wavefront gets frozen. This is from the point of view of like a photon. The wavefront doesn't move with respect to the photon. The interval between two ticks gets longer and longer as Astral Fane. Thank you for the galaxy. Much appreciated. W in the chat, y'all. I know it's a weird thing to say, but do it. Do it. The interval between two ticks gets longer and longer as m goes to 0. Basically, the ticks were overtaking the particle, but as the mass gets smaller and smaller, those ticks get slower and slower until it freezes. If m decreases fast enough, the geodesic particle clock stops ticking for n goes to minus infinity. That's the point. So that's why some particles and some geodesics have their clocks slow down so much that there's a finite number of ticks in an infinite amount of time. In the presence of two equivalent clock systems, the debate is open which clock system is best suited for description of physical reality. Yeah, okay, that's fair. The discussion on this issue was ongoing between Valery Rubikov and me. An advantage of geodesical physical time for particle clocks is its formulation for arbitrary metrics and arbitrary trajectories. On the other side, one may consider an advantage of the photon clock system that waves of massless particles as photons or gravitons exist for the beginning epoch of all realistic cosmology. So roughly, which is better, particles or photons for clocks? For the cosmic reference frame, the limit of a particle getting massless is smooth. Fine. Kitty. An open point for the photon clock is the formulation of a generalized cosmic rest frame for arbitrary inhomogeneous metrics. Okay, so we assumed that the space-time was very smooth and homogeneous, but in this case, maybe we shouldn't assume that. Oscillating wave functions for photons or gravitons exist for rather arbitrary metrics, at least if deviations from homogeneity and isotropy remain small. The issue concerns the choice of reference frames. For weak inhomogeneities of the metric, there are large families of trajectories for which the photon clock is time complete. As long as inhomogeneities are moderate, one may define an isotropic homogeneous rest frame by a suitable averaging of the metric. That's fair. Further work is necessary in order to clarify this issue. For most practical applications in cosmology, one can simply identify physical time for the photon clock system with conformal time for the background metric. For typical inflationary cosmologies, the universe is eternal, using a photon clock. In conclusion, the definition of physical time by counting oscillations of wave functions is well adapted to the beginning epoch of the universe when no observers with a measuring apparatus have existed. The discrete counting does not depend on the metric frame in contrast to proper time. For a given solution of the wave function, the number of oscillations, which corresponds to the number of ticks of a clock, depend on the trajectory in which the counting is done. This introduces the notion of reference frames in a wide context. A rather natural clock is the photon clock, which counts the oscillations of electromagnetic plane waves in the cosmic reference frame. For the cosmic reference frame, all clocks, defined by the oscillations of other massless fields as the metric. Wait, for the cosmic reference frame, all clocks defined. What does the sentence mean? For the cosmic reference frame, all clocks defined by the oscillations of other massless fields as the metric, or equivalently of the wave function for massive particles, belong to the same clock system as the photon clock. Oh, yeah. So if everything is, if you have a particle in the cosmic rest frame, then all clocks are the same as the photon clock. They can be mutually gauged to each other. The corresponding universal time can be identified with conformal time. Clocks in the cosmic reference frame tick an infinite number of times as one moves backwards for most common inflationary models. For these models, the universe is time complete or eternal. Geodesic physical time counts for massive particles moving on a physical trajectory the number of oscillations of its own wave function. The physical trajectories are generalized geodesics, which take into account additional forces for a space-time dependent mass. Okay. Geodesic physical time generalizes proper time for the case of varying mass. It sounds like a repeated sentence, roughly. In contrast to proper time, it is a frame invariant quantity. For certain cases where the particle mass or the scale factor vanished too rapidly towards the beginning of the universe, the geodesic particle clock stops ticking in this limit. This reflects the well-known fact that the rest frame is not well defined for massless particles. Okay, that's totally fair. The geodesic physical time can be defined for arbitrary inhomogeneous metrics and particle masses. For the photon clock, further work is needed for the generalization of the cosmic rest frame to arbitrary inhomogeneous metrics. Since massless particles, or effectively massless particles, are omnipresent in models of the beginning universe, the photon clock system seems to me to be the most useful definition of physical time. It can be used even if the beginning is characterized by quantum scale symmetry, where no intrinsic mass or length scale exists, and all excitations or fluctuations are massless. Okay. Oh. That's the end of the paper. Okay. What? All right. So that was abrupt. All right, so trying to think of how I can summarize. So it sounds like what they're trying to advocate for in this paper is something like, look, the mathematics works out for physical clocks, matter clocks. These are clocks that count their own wave function passing by them in a really nice way. However, in that picture, if you treat as physical time the number of ticks passing by a massive particle, the number of zeros of the wave function passing by a massive particle, that time doesn't go to infinity to the past. The clock stops ticking as you go further and further backwards. However, if you use a photon clock, it never stops ticking, and so you have time completeness. The trouble with the photon clock is that the mathematics are messier, and it looks like that there's not actually like a complete workout for that yet. It's hard if your universe is not super simple. And so I guess what they're saying is that we'd like to use the photon clock, but we don't know how yet. But we still think that it's probably the best clock because it works in these night situations. So I guess the idea here is more work needs to be done to try to understand the photon clocks in the early universe. It's a nice summary, though. I hope that they submit... They might be submitting this to PRL. Because it's only 6 pages long. And it's written like a PRL paper. So overall, I'd give it a 8.5 out of 10. Some things could use some better explanation. Maybe add a better conclusion. Break it up into sections. Good paper, though. I like it a lot. So for those of you who are watching on YouTube, thanks for being here. I'll see you next time. Dr. Blitz, the quantum